So we've seen some slides on Blockciphers already, but what a Blockcipher is essentially just a fixed function. So for every key it behaves like a permutation, which means that every time you encrypt the same message you will get the same ciphertext back. And one way to add flexibility to a Blockcipher is by using tweakable Blockciphers. And a tweakable Blockcipher, usually denoted with a tilde right here, tilde E, takes as input not only the secret key K and the message, but it also gets some value T. And this tweak is it can be seen as a public alternative of the key. And for every key and every tweak, the Blockcipher behaves like an ideal permutation. And tweakable Blockciphers find quite some applications. We've seen one on the previous presentation, but then for tweakable functions. And there exists some dedicated tweakable designs. One can, for instance, think of the hasty pudding cipher, Mercy and Treefish. Those are the classical ones. The focus in this work is on the modular design of tweakable Blockciphers, which means that if you are given a Blockcipher, a classical Blockcipher, try to construct a tweakable Blockcipher. And some constructions of this form are already known. Two of them already appeared in the original formalization of the tweakable Blockciphers by Liskov et al. Liskov et al. Introduced these two functions. So this is called LRW1, this is LRW2. What happens? I want to remove this mouse. Okay. So LRW1 makes two Blockcipher calls and just XORs the tweak in the middle. LRW2 makes one Blockcipher call and one universal hash function call. And the tweak is universally transformed using the universal hash function, and then this value is used as masking to the state. Related to the second one is in some way XEX, which doesn't use a universal hash function but a Blockcipher to transform the tweak. However, all of these constructions are only proven to achieve birthday-bound security. And this is a rather bad situation because we assume the underlying Blockciphers are perfectly secure, and then you essentially halve the security to get a tweakable Blockcipher. So the question is, can we get beyond birthday-bound security? And there is a construction known to get beyond birthday-bound security, and this is essentially by concatenating this one a couple of times. So if you concatenate this one an arbitrary number of times, in this case a row times, we have one big tweakable Blockcipher. It takes as input k row random keys and row universal hash functions, which should all be mutually independent. And this one turns out to achieve beyond birthday-bound security. In more detail, Landecker et al. Proved that if row is 2, so if you consider two cases, this one achieves security up to 2 to the 2n over 3. Actually, later Proctor pointed out there is a mistake in the proof, but he managed to elegantly fix this. A different result is from Lampe and Sorin, who consider a general case of an even number of rounds. So row can be general but even. And they claim that they prove that it achieves security up to 2 to the row n divided by row plus 2 queries. In fact, all of these authors conjecture the following bound, but as far as I'm aware, this one is still open. So if you look at the state of the art right now, we see the following, these 5 designs we've seen, and we see that one can approach this optimal security. Optimal security would be about 2 to the n. One approaches this optimal security, but only if the number of rounds in this LRW2 construction goes to infinity. So this means that you need an infinite number of Blockcipher calls and multiplications, which is of course not efficient. I think that even, well, LRW2 already makes 2 Blockcipher calls and 2 universal hash calls. So the question is, can we get better? Can we do better? So can we get better security with less primitive calls? And the answer to this question lies in the area of tweak-dependent rekeying. And this requires a little bit of further explanation. So in the original formalization of tweakable Blockciphers, Liskov et al. Suggested that for efficiency reasons, changing the tweak should be cheaper than changing the key. And the reason for this is, well, for efficiency reasons. One can, for instance, pre-compute the key to the Blockcipher. However, this is quite paradoxical in my opinion, because all of the schemes on the previous slide, they are designed with this criterion in mind. But if you design a scheme with this criterion in mind and you want to go for optimal security, then you need, well, 1,000 Blockcipher calls or something like this, or even 3 or 4 Blockcipher calls, and then it already gets inefficient. A different point of view was from, it was recently made by Jean et al., who consider it the other way around. So they say that, well, in fact, the tweak schedule should be stronger than the key schedule, and the reason for this is that the tweak is a variable the attacker can choose, but the key is always a random value. So if you combine these two principles, one sees that changing the tweak or the key should be approximately equally expensive. And this was essentially also used by Jean et al. In the tweaky framework, which has a key schedule that, well, some way nicely blends the key and the tweak. However, our goal is modular design, and there is a modular design that achieves beyond birthday bound security with tweak-dependent rekeying, which is the one from Minimatsu. So Minimatsu considered the following scheme. So it makes two Blockcipher calls. The first call is essentially to encrypt the tweak to get some subkey, and the subkey will then be used to encrypt the message. And Minimatsu proved that this construction achieves security beyond the birthday bound. It achieved security up to the maximum of 2 to the n over 2 and 2 to the n minus the size of the tweak queries. It is beyond the birthday bound, but only if the tweak is shorter than n over 2 bits. So this is a huge limitation. So if we now add this to the state of the art, we see that it compares quite well, in my opinion, but the tweak should be shorter, and it doesn't even achieve optimal security. And this brings me to the main goal of this work, and the main goal of this work is to construct, given any Blockcipher E, just any Blockcipher E and only this Blockcipher E, can we construct a tweakable Blockcipher that achieves optimal security? So for simplicity, we consider the case where all wires are n bits. So the key, the tweak, the message, and the ciphertext are n bits. But also the key input to the underlying Blockcipher should be n bits. Otherwise, the problem is trivial. One can just concatenate the key and the tweak. So this is the general design. If you go for a general question, one also needs a generic tweakable Blockcipher design. And we consider the following one. So we call it tilde E row, where row is the number of Blockcipher calls. In this picture, row is 3. It is based on 3 Blockcipher calls and arbitrary mixing functions A1, B1 up to B4 in between that process the inputs and the outputs to the underlying Blockcipher. Note that we need to put at least one condition on these mixing functions. And the reason for this is that this is a tweakable Blockcipher, so it should be invertible. So the mixing function should be designed in a certain way to make this scheme invertible. This is quite a technical requirement. I will not go into detail, but one can write down a requirement that assures that the scheme is invertible. But for the rest, these mixing functions can be anything. And we will not rely on these mixing functions to get security. So we will not assume that these mixing functions have any cryptographic strength. And we consider this scheme, we consider it in the information theoretic model, which is the customary model for this generic approach. And in this model, we consider a distinguisher D. This distinguisher has access to either this generic construction tilde E row or a random tweakable cipher tilde pi. And the distinguisher is also given additional access to this ideal cipher E. This may remind of the presentation from Yannick Sorin, where he uses more or less a similar model for key length extenders. It's also information theoretic indistinguishability. I want to note that some results in the area are also in the complexity theoretic setting. And later in the presentation, I will come back to this complexity theoretic setting, but for now, we consider information theoretic indistinguishability. Okay. Sorry. So our goal is an optimally secure scheme, but first of all, it should also be efficient. So the first step to consider is, of course, row is 1. We consider one tweakable Blockcipher based on one ordinary, one classical Blockcipher. And in the ideal case, these mixing functions are also linear. So in the optimal setting, we would get a scheme like this that achieves perfect security, where A1, B1, and A2 are linear. However, in this case, we derive a negative result. In more detail, we show that if A1, B1, and A2 are linear, this construction can be distinguished by an information theoretic distinguisher in at most 2 to the n over 2 queries. So for any mixing functions, A1, B1, and A2, one can attack this in the birthday bound or faster. I will not explain the attack, I will just give the high-level idea. So what we essentially want is we consider a distinguisher that can make queries, and we try to find a relation among these queries that is very likely to occur for this construction, but unlikely for the ideal tweakable permutation pi tilde. And then we make a distinction depending on how A1, B1, and A2 process the key, the tweak, and the message. So that's bad news. We cannot get an optimally secure scheme like this. What's the next step? We would still want a scheme with one block cipher call, but we may release this linearity condition. And this brings me to the first design, which is tilde F1. And tilde F1 is the following design that makes one block cipher call and one multiplication. And we use the key and the tweak both for the keying to the block cipher and for the masking of the state. So in more detail, the key will be the key to the block cipher will be k XOR t, and the masking will be k times t. And for this construction, we managed to prove security up to 2 to the 2n over 3 queries. I will explain the proof idea on the next slide, but let's first summarize the cost. So we see it makes one block cipher call, one multiplication, a couple of XORs, which are basically for free, and it makes one rekeying for every new evaluation. So that's the cost of this scheme. So regarding the proof idea, I will explain the high-level idea. I will skip the technicalities. Recall that this is the scheme. I removed all parameters t, m, and c. The key is still there. The key is a secret value, so key is chosen and secret. Now consider any construction query that the distinguisher makes. Now consider any construction query that the distinguisher may make. A construction query is of the form tm, so a tweak and a message to get a ciphertext, or the other way around. The tweak will appear here, the message will appear here, and the ciphertext will appear here. But using the secret key, this construction query can be equivalently described as a block cipher evaluation. In more detail, it corresponds to a block cipher evaluation with key input k XOR t, message input m XOR k times t, and ciphertext output c XOR k times t. Okay, so this is a construction query, but the distinguisher can also make primitive queries. And it may be the case that this one collides with a primitive query. A primitive query is of the form L, X, and Y, where L is the key input, X is the the primitive input, and Y is the ciphertext output. And they may hit these two queries. In more detail in the paper, we prove that as long as these two queries, as long as no construction query ever collides with a primitive query, everything is perfectly fine. So what we need to do is we need to bound the probability that any construction query hits a primitive query. And note that, well, as becomes clear from the picture, a construction query hits a primitive query if the key XOR the tweak, it's already empty, equals L, and m XOR k times t equals x, or in the inverse case, if k XOR t equals L and c XOR k times t is y. Recall that the distinguisher can make forward and inverse queries. Now we can plug in the first equation, so this equation, into the second one, and we can equivalently describe the problem as follows, where we consider the probability that any construction query and any primitive query satisfies one of these two conditions. Now for the sake of the presentation, focus on the forward case only, so we've only focused on this case. And we consider the probability that this happens for any construction query and any primitive query. And for this, we use some ancient result from mathematics, and it is the Semeredi-Trotter theorem. I hope I'm pronouncing the names well. But what the theorem essentially says is the following. If F is a finite field, consider the two-dimensional finite field, and let L be some subset of lines in this field and P a subset of points, then the number of point line incidences, or in other words, the number of points that appear in P that appear in a, let me repeat, the number of points in P that appear on a line in L is upper bounded by this minimal term. I will not prove the theorem. For people interested in the theorem, I would like to actually refer to another paper in crypto, namely by Jetchev et al., who introduced a double-length compression function also using this result. However, we will use the result slightly differently. What we will do is the following. It turns out that if we identify the construction queries as lines and the primitive queries as points, we can apply this theorem and see that there are at most q to the power 3 over 2 solutions to this right-hand equation. So if the attacker makes q queries, there are at most q to the power 3 over 2 solutions to this equation. But any such choice, any of these q to the power 3 over 2 choices, uniquely fixes this value L, X, or T. But the key is a random n-bit key, so then it turns out that this key satisfies that equation with probability at most q to the power 3 over 2 divided by 2 to the n. Hence, we get security up to 2 to the 2n over 3 queries. So that's the basic proof idea. The technicalities are in the paper, but so far still no optimal security. And this brings me to the second scheme, and in the second scheme we consider a tweakable block cipher based on 2 block cipher calls. In more detail, we consider the following scheme, which we call tilde F2. Tilde F2 looks like the previous one, but the only difference is in the way the masking is done. So where in the previous slide the masking was k times t, in this time we encrypt the tweak under the key to get this masking value, the masking value right here and on the other side. And for this construction, we managed to prove security up to 2 to the n queries, up to a very small constant, essentially, but roughly security up to 2 to the n queries. Before going to the proof idea, again, let's summarize the cost. It consists of 2 block cipher calls, some XORs again, no multiplications, and every new evaluation requires to rekey the bottom block cipher. So for the proof idea, we can do the same approach. So we have this scheme, we plug in any construction query and a primitive query, and then one sees that any construction query hits a primitive query if either of these 2 settings holds. So either k XOR t equals L and z XOR m equals x, or the inverse variant, where z is a subkey. And how do we proceed now? It turns out that there are some technicalities because z is a subkey and z is derived based on the key and the tweak. However, in the paper we show that, well, the key is a random value, but we show that z is also an almost random subkey. And using this we can get optimal security. So for the technicalities I would like to refer you to the paper, but this is the baseline of the proof. So if you now compare the 2 schemes with the other ones, I've added them in the bottom, we see that they, well, in my opinion, compare quite well. If you compare, for instance, 2 rounds of LRW2 with tilde F1, they achieve the same security, but the key size is much smaller, and the tilde F1 makes 1 block cipher call, 1 multiplication, and 1 rekeying, which essentially means that tilde F1 is cheaper than 2 rounds of LRW2 as long as the rekeying is cheaper than a block cipher call. Similarly, for tilde F2, it achieves optimal security, and if you compare it with an infinite number of rounds of LRW2, tilde F2 only makes 2 block cipher calls and rekeying. On the downside, these 2 schemes are proven in the information theoretic model, while the other ones are proven in the complexity theoretic model. So that's a difference in the proof approach. And what do we, if I may elaborate on this, what we have done essentially is the following. So we consider tilde F alpha for alpha, one of the 2 designs, with an ideal block cipher E, and we compare it with the ideal tweakable cipher pi tilde. And what we should have done in the complexity theoretic model is we consider tilde F alpha with any block cipher E, and we compare it with an ideal tweakable cipher pi tilde. And how this can be solved, how essentially all proofs in this area go. The first step is we replace this any block cipher by an ideal block cipher E, and at the end we add the PRP or SPRP security. Unfortunately, it doesn't work for this proof, and the reason for this is that the key is tweak dependent, so the attacker can adjust the key. And this means that you would officially require the XOR related key security of the block cipher. So a complexity theoretic proof is possible, but I want to stress that this bound is unnecessarily loose. Things are getting technical now, but the idea is that in our scheme, if the attacker chooses a different tweak in order to adjust the key input to the underlying block cipher, this will also influence the masking. And this is not taken into account in the XOR related key security. So things are getting technical now, but in the paper we essentially show that this, well, is a loose step. But nevertheless, it is possible to get a complexity theoretic proof. And this brings me to my conclusions. I've got 10 seconds, but so we've introduced tilde F1 and tilde F2. I think they are very simple schemes with very few primitive calls. And they achieve high-level security up to optimal security for tilde F2. And in my opinion, they're more efficient than the other schemes as long as key renewal for the underlying block cipher is relatively cheap. The work leaves some interesting questions for open questions for further research. One of them would be, can we construct another scheme, a one-call scheme with better security? So our one-call scheme makes a multiplication and it only achieves 2n/3 security. Can we get better security, maybe using 2 multiplications or multiple keys or something different? A second question would be quite an important question. Can we avoid this related key security condition? It may be possible, maybe using the trick that Minimatsu used in his scheme, or in other words, maybe using a third block cipher call. However, this will degrade the efficiency. And third question, a third point for further research is to compare implementations of these schemes with the existing constructions. So that's the end of my presentation. I would like to thank you for your attention.
Thank you very much. So, any questions? Okay, so maybe I have one. So, you mentioned about the related key security condition on the underlying primitive.
Yes.
And I wonder if you can say something about the related key security for the whole construction.
I should be able to do, but not right now. I didn't analyze this. But I don't know of any attack. So I didn't, well, I quickly looked at it, of course, because otherwise, if you have a stupid attack, then you shouldn't write it. But I didn't see any attack in this case.
Okay. Other questions or comments? Okay, thank you very much.